All right, so I have three. Well, we can generate infinitely many possible, infinitely many social welfare functions, but these are sort of the standard welfare functions that our textbook also refers to. So the classes, let me first talk about these welfare functions, their properties, and then I'm going to show how they work through an example, a numerical example. So the classical utilitarian social welfare function. So whenever you see SWF, it means social welfare functions. And the second one is weighted sum of utilities social welfare function. And the third one is the Rawlsian social welfare function. All right, so the utilitarian social welfare function, basically, so given the preference profile or the profile of utilities, the social utility is basically just the summation of the each agent's utility, all right? As we did in the summing the profit functions, the profits of each firm, all right? So for every alternative, the social utility of that alternative is the sum of the utility values of the agents for that alternative, all right? The weighted sum of utilities, however, again, we sum all the agents' utilities, but before we sum them, we multiply each agent's utility with an agent-specific number, alpha I. We usually assume that alpha I is some number between 0 and 1, all right, for every I, assuming that we have n many agents, n is greater than or equal to 2. And what matters, or what's important, is that alpha 1 plus, doesn't have to be the second condition, but usually that's what it makes. Alpha 1 sum all the way up to alpha n equals to 1, all right? So if, for example, each alpha I is equal to 1 divided by n, it gives the same weight to all agents. All right. However, if alpha I is different than 1 over n, it means it's going to give more weights to some agents and less weights to other agents. All right. Well, what is the intuition behind this? Sometimes as a policymaker, you may want to consider the welfare of some of the agents more than the others. For example, if we are talking about, so if those n agents are a member of a board of a company, and those board members are voting which strategy to follow for the next 5 years, well then probably some of those board members will have higher share of the company than the others. So for example, say one of them owns 70% of the company and all the other members equally split the remaining 30%. So usually it happens that the 70% guy who is the owner of the majority owner of the company should have more say regarding the company policies. So therefore, as the social planner, you may want to put more weight to some agents and less weight to other agents. So you basically care some agents more and care other agents less. If this is the scenario, well, you can use those social welfare functions. By the way, the utilitarian social welfare function and the weighted sum of utilities social welfare function, in a sense, is equivalent if alpha I for each individual is equal to n. All right? And then final example, the Rawlsian social welfare function. Well, given the a profile of utilities, the social utility of an alternative is equal to the minimum of the utilities of the agents for that alternative. So we basically look at the agent whose utility is the lowest for that alternative. And so always, for all the alternatives, the social utility is the one that is what we call the worst off agent. I mean, the agent with the lowest utility, because that's the agent that I would like to take care the most. All right? So think about this, a population, and there's a very strong unfairness within the population. And so I would like to make sure that I'm going to pick a policy which is going to benefit the most needy group of agents. And so in that case, using Rawlsian social welfare function makes more sense. All right? Okay, so let's apply those social welfare functions on this simple example that I just wrote. So I have 3 agents. I call them A, B, and C. I have 3 alternatives, X, Y, and Z. My Y is weird. All right? And these are the utility values. All right? So this is utility of agent A for alternative X. This is utility of agent A for alternative Y. This is utility of agent A for alternative Z. And this 100 is the utility of agent B for alternative Z. This is utility of agent B for alternative, Y. And this is utility of agent B for alternative X. And then finally, as you can guess, this is these are the utilities of agent C, all right? Z, Y, and X. Okay, so the classical utilitarian social welfare function. So how does it operate? The welfare function, the utilitarian, so let me denote it as WU. What is the social utility for alternative X? Well, you're just going to add the utilities of all the agents for that particular alternative. So basically it means UAX plus UBX plus UCX. All right? Well, what is the social utility of alternative Y? Again, you're going to add up the agent's utilities for that particular alternative, Y. UCY. And similarly, the social utility for alternative Z is UAZ plus UBZ plus UCZ. All right? So the rest is very simple. UAX is 100, UBX is 50, and UCX is 70. All right? So in total, this is going to be equal to 220 units of utility. And what about alternative Y? It's 50 utility point for A, 70 for B, and then 40 for C. So this is 110, 160. Again, I hope I don't make any mistake, but if I do, well, forgive me. For alternative Z, it's 70 plus 100 plus 80. So this is 180, 250. So it means the social utility of the alternatives according to utilitarian is as this. So X is 220, Y is 160, and then Z is 250. So according to the utilitarian social welfare function, it means which alternative is the best? Alternative Z is the best, all right? So that's what it means. So Z is the first best, and then X, and then Y is the worst alternative, all right? Okay, well now let's apply the weighted sum of utilities. Well, for this, in order to be able to use it, I need to define the weight. So what is the weight? Well, don't make it one third, because it's going to give us different values, but exactly the same ranking between X, Y, and same ordinal ranking between X, Y, and Z. So let's give the following example. Say alpha 1 is equal to 1/2, and alpha 2 equals 1/4, and alpha 3 is equal to 1/4. All right? So the half of the company is owned by agent 1. The remaining half is split equally between agent 2 and 3. If this is the case, well, what is the social utility? So let's denote this WW, all right? So the weighted sum of utility social welfare function for alternative X is 1/2 times agent A's utility for X plus 1/4 agent B's utility for X plus 1/4 agent C's utility for X. All right? Well, what about the social utility for alternative y. Again, the alpha 1 is 1/2, so 1/2 UAY plus 1/4 UBY and then 1/4 UCY. So you get the idea. So I'm not going to write it for Z. I'll just write the numbers. So let's do the math. So UAX is 100 divided by 2, it's 50 plus B plus C, which is 120 divided by 4, which is 30. So the total is 80. For Y, 1/2 of this, 50 25, plus quarter of 70 plus 40. 70 plus 40 is 110. 110 divided by 4. Well, let's leave it as such. 110 divided by 4. So if you add them up, so this is 25 times 400. So 210 divided by 4. All I know is that this is more than, I can calculate it, but forget about it. So this is more than 50, but less than 60. It's definitely less than 80. And then finally for Z, it's going to be 1/2 70 plus, 1/4 100 plus 1/4 80. So basically this is 35 plus, this is 280 divided by 4, okay? Which is 140 divided by 2, which is 70. So this is 105. All right. Again, if I do a mistake, I apologize. This is the best I can do as I speak and at the same time do the math. So sometimes I make mistakes. So if those numbers are correct, then the WW is going to give us X80 utility value, social utility. This is 210 divided by 4, and this is 105. So it seems like Z is still the best alternative, and then X, and then Y. So exactly the same ordinal ranking. All right? So this is how the weighted sum of utilities would work. And then finally, Rawlsian social welfare function. So how does it work? Well, so let me clean this up. Okay, so I'm going to call it W Rawlsian. So what is the social value for X? Well, it's the minimum of the minimum utility among those three agents for the alternative X, meaning the minimum of UAX, UBX, and then UCX. Whichever is the min will be the social value. Walrasian value, social value for Y is the minimum value of UA Y, UBY, and then UCY. All right, so you get the point. So I'm not going to write it for WRZ. I'll just write the numbers. So what is UAX? It's 100. So this is equal to minimum of 100, 50, and then 70. So obviously the smallest one is 50. So the utility value for X will be 50 according to Rawlsian social welfare function. Well, what about this one? The agent A's utility for Y is 50, agent B's utility for Y is 70, and agent C's utility for Y is 40. So therefore Y is going to get utility value 40. And then finally for a Z, it's going to be 70, 100 versus 80, the minimum of those, which is 70. So the W Rawlsian is going to give us the utility function 50 for Y 40 and then Z 70. And interestingly, it also gives us Z as the most preferred, socially most preferred alternative, and then X and then Y. All right. So, well, this is a coincidence. All right. That obviously these, if we change those numbers, we will I mean, at some point receive different, I mean, certainly different utility values, but certainly different ordinal rankings between the alternatives. So because those social welfare functions are different from each other, I mean, not always maybe, but sometimes they will give us different social rankings between alternatives, all right? But in this very specific example, this is how these three social welfare functions work. So I know it's been already 15 minutes, but let me finish by saying the following. The social welfare maximizing allocations, might be more than one, are always Pareto-efficient. All right? So here, in this very specific example, the social welfare, so whichever social welfare function we use, the social welfare maximizing alternative, the allocation, is Z, right? Because Z is the first best. So therefore, Z must be the Pareto-efficient allocation, Pareto-efficient alternative. Well, how do I check that? Is Z really Pareto-efficient? Well, in order to check this, all I have to look at is the agent's preferences over X, Y, and Z. All right? And so I should ask myself the following question. So let's say I give these agents Z. All right? Well, is there another alternative other than Z, I mean it's either X or Y, which is going to make all agents better off? Is it possible? Well, let's check. So if I give those agents Z, agent A is going to get utility 70, agent B is going to get utility 100, and agent C is going to get utility 80. I don't know you, but isn't it obvious that Z is Pareto-efficient because Z gives agent B the highest utility he can ever receive, which is 100. If we give Y or X to the agent B, I mean to those guys, I mean A, B, C will receive the same X, all right? So that's allocation applies to everyone in the society. So there's a policy and the policy applies to everyone. So it's not like I give one agent one policy, another agent another policy. So one policy, so it's like these are X, Y, Z are presidents of the United States or Canada. And so if we, I'm not voting for Trump, but if Trump will be the president, well, it's going to be the president of all the voters, all right? Whether you like it or not. So therefore, it's not like somebody gets the president as Biden, the others get the president. So there's not going to be two presidents. There's going to be only one president. So here, if we give, if the outcome happens to be X, the agent B will certainly get worse off. If we give the outcome as Y, again, agent B will get worse off, all right? Maybe the others will be happier, all right? But agent B actually receives the highest utility by receiving, by this alternative Y. So alternative Z, So Z is Pareto-efficient. Z is Pareto-efficient. PE stands for Pareto-efficiency. Z is Pareto-efficient for this particular preference profile. All right? Let's check the following. Is X or Y are Pareto-efficient? Let's see. X is Pareto-efficient. Again, I think it's obvious because agent A this time receives the highest utility ever through X. If we give a different president to him or her, she will certainly get worse off. So 100 is definitely better than 50 and 70. So any other alternative is going to make A worse off. All right? I mean, for example, if we give them Z, clearly agent B will love that. And clearly agent C will love that. However, it will certainly make agent A worse off. So there's no way to make one agent better off without making other agents worse off. All right? So therefore, X is also Pareto-efficient. Okay? And then let's check Y. So Y is never the best alternative. So is there an alternative that will actually improve all the three agents' utilities? So if we give Y, agent A is going to make 50 utility, agent B will make 70, and agent C will make 40. But instead, if we give them Z, all right, agent A will be happier, right? Because from 50 to 70, it's an improvement, more utility. Agent B will also get happier, and agent C will also get happier, you see? So Z is predominating Y. So Z is a better alternative for everyone, and no one will actually say, hey, Y was better. No, no one will say that. So everyone, all the agents will say, oh yes, Z is definitely superior than X. Than Y. So therefore, in this very specific example, Y is not Pareto-efficient. Okay? Which kind of makes sense, because whatever social welfare function we used, right, Y was never the social welfare maximizing allocation. Instead, Y was always the socially worst alternative. And, well, it happens that it is not Pareto efficient. I hope that was clear.